So is this just some description of our chemical bond, the covalent chemical bond? The chemical bond is holding the atoms together, forcing the atoms to behave as a unit so they move together, stay together. This comes from the tendency of the universe to seek the lowest possible energy. So that means that the chemical bond is lower energy than the atoms separate from each other. An example that would be for fluorine. Fluorine atoms release 77 kilojoules per mole when we form the bonds for diatomic fluorine. We're going to go into valence bond theory, another type of a localized electron model, where that means that we're keeping our electrons on atomic orbitals in the individual atoms. In this theory, we are saying that the covalent bond is formed by the overlap of these atomic orbitals from the separate atoms. And the bond is formed by the attraction of the electrons to the nucleus. So each nucleus is attracted toward that pair of electrons in between the two nuclei. We define zero energy as atoms that are infinitely separate from each other. As they approach each other and start to overlap, if they are favorable for bond formation, then the energy drops down. This is the attractive energy from the nuclei to the atoms, to the electrons, from the nuclei to the electrons of each atom. After some minimum, we're going to start to end up getting an increase in energy. This increase in energy, which ultimately becomes repulsive, is the repulsive energy between the two nuclei. So there's a minimum energy well where the two atoms can reside and be stable, form a stable bond. So the atom, though, won't just sit right at the very bottom, the pair of atoms. So if they have this much energy, then they will be oscillating, vibrating between these two distances. So the atoms aren't still at one particular distance. So when we're talking about bond distance, that'll be an average of the distances. And we, of course, look at the lowest energy state possible, but they're still oscillating within that well. Our atomic orbitals do not give us the shapes that we see. We cannot get a 120 bond angle using SPD atomic orbitals. So what we're going to do is hybridize the atomic orbitals. Mathematically, we would do this. It'd be called linear combination of atomic orbitals. So we're going to take some atomic orbitals, blend them together to create new atomic orbitals. And what happens is that the number of orbitals that we start with will give us the number of orbitals that we end up with. So if we start with 2 orbitals, we're going to end up with 2 orbitals. If we start with 3, we're going to end up with 3. But we're going to end up with a different combination of these orbitals, which will give us different geometries of these orbitals. Now we've been saying that we can have 1, 2, or 3 pairs of electrons in a bond, a single, double, or triple bond. Well, we have 2 types of bonds, a sigma bond or a pi bond. Every bond starts with a sigma bond. A sigma bond is the overlap of orbitals right on the bond axis between the 2 nuclei. So between the 2 nuclei, we're going to have an overlap of our atomic orbitals, and this is going to be our sigma bond. Our pi bonds are going to come from unhybridized orbitals, normally unhybridized p orbitals, so these orbitals have lobes above and below the bond axis. These orbitals above and below the bond axis are different phases of the electron, different signs of the electrons. So if we have adjacent atoms with occupied p orbitals, they will overlap. In this case, the density will be above and below the bond axis. It's not on the bond axis. In fact, since these are above and below or different phases, that means that there will be no electron density on the bond axis. So our electrons are just above or below the bond axis. This is our pi bond. So a single bond is always going to be a sigma bond. A double bond is going to start with a sigma and then have a pi bond. And a triple would be a sigma plus 2 pi. So in this molecule here, carbon dioxide, we have two adjacent double bonds. See, the central atom will have two p orbitals participating in the pi bonding, but on different atoms. So one p orbital is above and below the bond axis, and the other p orbital is in front and behind. So when we have a triple bond, we're going to have the sigma in the center right on the bond axis, one pi above and below, and a second pi in front and back. Okay, so for doing a sigma bond with an unhybridized orbital, unhybridized atomic orbital, if we're doing bonding of hydrogen, H2, we're just going to be bonding our 1s orbitals together. Those two 1s orbitals overlap in between the two nuclei, and that is creating our sigma bond between the two hydrogen atoms. On a period 2 element, we can have overlap of the p orbitals. And for the overlap to occur, they have to be the same sign. The p has two different signs available. The s has two different signs available in time. P has two different signs available in space. So when the two of the identical signs are overlapping, they create a big lobe, overlap lobe between the two nuclei, and this is our bonding between the two atoms. So when we're doing two p orbitals that are perpendicular to the bond axis, the overlap is going to be above and below the bond axis. This is our pi bond. So we have a overlap above and below. These are different phases or signs of the phase, which means that we have a nodal plane on the bond axis, meaning that our electron density goes to 0 on the bond axis. And that is for a pi bond. So for our bonds, as we increase the bond order, go from single to double to triple bonds, our bond length is going to get shorter, and our bond strength is going to get stronger. So a double bond is going to be shorter and stronger. A triple bond is going to be shorter and stronger. So to describe the geometry of the molecules, we're going to hybridize our bonding orbitals for the sigma bonds. Our pi bonds are going to be unhybridized p or d orbitals, but our sigma bond is going to usually be hybridized orbitals.